My name is Enge Wang, and from the Peking University, and also chairs the advisory committee for the Institute of Physics, Chinese Academy of Science. I worked as the director of the Institute of Physics many years ago, and later moved to the Peking University as the president. 4 years ago, I moved to the Chinese Academy of Science as the deputy president, so I already stepped down last year. In the past 20 years, I moved my research to study the interfacial water, means the water on different solid surface. The water is the most simple things and in nature, and so I use this title, the soft in nature and hard in science. So why, so is such simple materials in nature, but it's still a mystery to science. The reason is very simple, and the more we look the water, the more the problem accumulate. So that's very strange materials. So why? Basically, you know that the water is composed by the light materials, the hydrogen and the oxygen. And basically, you can see we need to treat the nuclear equal as the electron. So this is a very basic challenge for many years. And so the following talk is a combined effort, both the theoretical and experimental studies. In the theory, we first need to back to the original Schrödinger equation. So, as you can see, the nuclear cannot be treated as a classical particle. Instead, it's a polymer. So in this way, we treat the nuclear as equal as the electron. And also, it's a challenge in the experiment. The current most sensitive technique is just for the electrons. So in this part of work, we develop a Q+ technique. So by using this technique, the current setup can be sensitive also to the nuclear. So this is another challenge. So I used both the theory and experimental techniques to study the following water things. So here I just use few examples to tell you how the methods are powerful to explain what the water look like. So after each example, I listed some of the reference for your further interest. The first example is to try to give the submolecular image of water on the simple material surface. And actually, this is a really hard topic in the past 20 years, maybe even longer than that, ever since the discovery of the STM. And here I just summarized the most interesting results in the past years. And basically, you can have some idea what the water look like. The first, the water molecules on the surface is just like the blue-red spots. So you cannot see any inside structure from the blue-red spots. And anyway, by using this technique, we can number how many water molecules in the water cluster. For example, you can see 1, 2, 3, 4, 5, 6. So for this kind of water cluster, it contains 6 water molecules. But another thing is we still cannot, the water molecules when they form the cluster, they will connected by hydrogen bonding. However, based on this experimental observation or image, you cannot see the bonding directions, but this shows clearly it's a clockwise bonding. It's connected, it's computer simulation result. So both are the challenge. We've seen to now why the water is not easy to observe on the surface. This is the theoretical simulation given by the Materials Shufflers group in Berlin. And basically you can see that the water orbitals are far away from the Fermi level, at least 5 EV below the Fermi level, as shown here by the red curves. And even worse, you'll find that the density of states in the Fermi range is come from the substrate. the metal substrate. So with these two difficulties in mind, we try to improve the experiments. First, we try to reduce the water-substrate interactions. So in that way, you can see we're still using the metal substrate, but cover the surface with the sodium chloride to 1 mole a year the sodium chloride. So this is very important, is the insulating thin film. And the second, we put the tip very close to the water molecules. So in that way, we can increase the coupling, then move the water orbital towards the Fermi level. So that's the trick. Now, what we can observe in the experiments, basically you can see there's some fine structures from the internal water molecules. We believe they should have some relationship with the theoretical simulation, means the density of states. Yes. Now, with further system study, we find that this image actually corresponding to the HOMO state, and this image corresponding to the LOMO state, and the last one corresponding the mixture between the HOMO and the LOMO. So that's very interesting, and I have to say that's the first time the people can see the inner structure from a water monomer. So that's a very exciting result. So encouraged by the previous study, now we try to move further to see if we can see the hydrogen directionality from formed water clusters. And now we've dropped the clusters to the water monomer on the surface at 5K with quite low temperatures. You can see there's many water monomers. Then we use the tip to move the water monomers to form the cluster. And finally, we find some tetramers on this kind of surface. By using this STM, we got this high resolution image. But it's still difficult to tell you where is the hydrogen directionality. Now, we change the tip, and in other words, we functionalize the tip with some chloride atom as the tip. And the following cartoon shows how it works. Now, we use a clean tip and heat the surface and pick up a chloride atom. Now we use this one as a new tip to study the image. So this is very interesting. Okay, the technique is very helpful, and you can see the left column shows that use the clean tip, and that's the DIDV curve, and this one comes from the functionalized tip. So basically, you can see that for each water monomers, molecules inside the cluster, the density from the dark to the bright, from dark to the bright. So in this way, we can carefully compare with the theoretical simulation. And you can see that this is the simulation results and this is the experimental result. So basically, we know that for this tetramer, they have anti-clockwise chiralities. So it's clearly the directionality of the hydrogen bond. And for this one, corresponding the clockwise chirality. So that's very interesting. For the tetramer on the sodium chloride surface, when they form the cluster, they can have two chiralities. So this is the first time we show the people how when they bonding together from the cluster, they have different directionality. So that's very interesting. Now, we quickly move to the second example to see the full quantum tunneling of the protons. Now, with the tetramer, the tetramer, we already proved that they have two different chiralities. So we've been to changing the knowledge and to see if we can control the chirality by the experiment. So this must be very interesting study. And basically, we found that when the tip is far above the surface, the tunneling current is kept as constant. Now we move the tip towards the surface, then the current is oscillation between the clockwise state and the anti-clockwise state. And finally, when we move the tip away again, they keep the final state as constant. Now, I'm using the following cartoon and see how it works. Okay, now you can see when the tip is far away from the top, it's constant the current keeps it constant. When the close to the surface, there's an oscillation, means the chirality is changes. That can be controlled by the tip. And finally, when we move away back to the final state and keep the state for a long time. Now, to make a quantitative study, we have counting how many events happen for a given time. And you can see that can be summarized by the shadow in this figure. And this result can be well described by a simple formula. The inverse of the tau is just means the switch rate from the clockwise state to the anti-clockwise state. And you can do another way from anti-clockwise state to the clockwise state. So this is very interesting. Now, we try to see if there's some influence in the experiments. The first, we have changes the bars, means to change the electric field, and also to see the tunneling changes. And basically on this figure, you can see that when we change the bars, the switch rate keeps as constant. So that means there's no electric field influence, and also no hot electron influence. Yeah. Now we change the substrate temperature, can see, and we try to see if there are some other influence. However, when we change the temperatures, again we see that the switch rate keeps as constant. So it means there's no thermal effect in this experiment. Now finally we replace the hydrogen by deuterium, and you can see the oscillation is disappear. So that means the strong isotope dependence and can be observed here, which is dominated by the quantum tunneling results from the nuclear quantum effects. So that shows clearly the proto-tunneling influence by the nuclear effect. Okay, now, so furtherly, we can also study the switch rate as a function of the tip height. So basically, you can see the dependence is non-monotonic in this study. And you can see the difference between the clockwise states to the anti-clockwise states, and with that, from the anti-clockwise to the clockwise states, there is some difference. The reason is very simple, because the STM tip is not exactly in the center of the tetramer. The far away from the center, the bigger the difference. So that comes the difference. So to understand what happens in the experiments, we have studied the different transition mode. This is one of the example. We call this the stepwise proton transfer. So you can see from the original stage, in the first step, one of the proton left the water molecules to the neighbors, and in the next step, they pick up from the neighbor, and in this way, they finally change the chirality. This is initiation is anti-clockwise state, and finally to the anti-clockwise state. However, for this kind of transition, the energy barrier is too high. It's something about 2 eV. This cannot be observed in the experiment in such a low temperature, just several cases. Now, we move to another possible model. We call this is the rotation model. In this case, the proton not leaving during the transition, the proton not leave the water molecule. Instead, they line up and the rotation, and finally changing their chirality. You can see in this way, they can at the beginning in this way, and the rotation a little bit and to the middle, and then change it to another side. So in this way, however, when we calculate the rate dependence, we find it's monotonous dependence. So that's different with what we observed in the experiment. We tried different model, and finally we find when they form the tetramer during the vibration, the lattice is braced at the surface. When they get closer, the proton is just in the middle of this lattice. When the lattice gets larger again, they're broken in another side. So in that way, it changes from the anti-clockwise state to the clockwise state. And the energy barriers needed in this processing is just 0.8 eV, and it can be even lower in that study. So this is very interesting. And even more, we calculate the switch rate as a function of the tip height. And you can see it's quite a good agreement with the experimental observations. Okay, now we try to see if there are collective proton transition. And this has been challenged for more than 10 years. And in this study, we have carefully, the STM is a very localized technique. We can study every water monomer on the surface. And in this case, we use another technique. We call this tip-enhanced inelastic electron tunneling spectroscopy. And again, I use the following cartoon to explain how it works. Sure, okay. When the tip is far away of the surface, above the surface, the vacuum barrier is quite high. So when the close to the surface, the barrier is narrow. And in some case, we end the bars, and you can see they continue and we end the bars. So there are some electron tunneling through the vacuum gap. We call this is elastic tunneling. When we continue to increase the bars, the home level is close to the Fermi level, and some electrons tunneling through the HOMO state. We call this is the inelastic tunneling. Now we record this tunneling curve, and then we can get such kind of spectroscopy. Then we can identify the peak. For example, this one corresponding to the switch mode, this corresponding bonding mode, and this corresponding to the rotation mode. So this is the first time we can study, by using this technique, the hydrogen bonding chance for each individual water monomers. So in this way, we can identify that for the water, the number 1 water is water, and number 2 also number 3. However, this here you can see the H replaced by the D. So this is can easily see which is water, which is deuterium replace the H. So in this case, we make attachment again, but with one is different with the H02. So in this case, we can form different attachments with one deuterium water monomer, or even with 2, 3, or even all the 4. So this is a very detailed experiment. So now we study the switch rate, and here shows the final result. If there the attachment formed by the four water molecules, you can see the switch rate is quite high. When we replace one of them, the switch rate can be reduced at least half. So this is a clear experiment, and shows that the collective and the quantum nature of proton transfers. So that's very interesting. Now, the reason in the theoretical simulation, we can see what's the reasons. When this attachment is formed by all the water molecules, you can see the barrier is very low. When we replace one of them, the barrier increase is quite high. So this is the simple reason, but there is a debate for more than in the last 20 years. Okay, now we move quickly to the final example. We try to improve the techniques by introducing the IAAM. In this case, we develop this kind of setup, and which is very sensitive to the high order electrostatic force. Now, by this technique, we can easily identify in the experiments, this is the oxygen, this is the hydrogen. So this is a very powerful technique. By using this technique, we can identify different structure of water clusters, and we can easily see either they can tilt up or down, or fly on the surface, or even tilt towards the surface. So this is a very detailed experiment for the water cluster from the monomer to few water molecules. Now, then we try to see, there's a lot of ions in the waters. So usually they can form different high trees. In this study, we have see with the first example, we try to see the sodium ions. Can see how many water like to make the shells surrounding the sodium ions. Now I using the following cartoon and see how we do in the experiment. Okay, this with the tip close to the surface, we can pick up a chloride atom and use this functionalized tip and then move the water towards the vacancy. Now we pick up another sodium ions. When this then move on the surface, when they meet some of the water, then they can be left towards attracted together. Now we can move more waters towards this cluster. That's the dimer and the trimer, and even make the attachment, and then we can even make another different structure. So by using this technique, we can carefully classify how many hydrides surrounding the sodium ions. In this case, you can see there's 1 water, and there's 2 water, and 3 water, 4 water, and 5 waters. So this is very interesting. By using this technique, we can see how this is the first time proved in experiments, and is over more than 100 years. Okay, now we studied in the first clusters. We try to see how there's mobilities for such kind of hydrides, and it's very surprising to see that based on this experimental study, we find that the mobility for the sodium ions with 3 water, the mobility is very high, even at the room temperature 300 K. So this is really magic numbers, and we also try to understand what's the reason in the theoretical simulation, and basically you can see that when the sodium ions with 3 water molecules, there's mobility, the barrier is very low, so the mobility is higher. Okay, yes, and you can see, and the barrier can be low as 80 MeV, so that's quite low barriers, and this shows why the clusters are very easily to move on the surface. And this just shows you the cartoon. When the water when the sodium with 1 water, you can see is very localized. It's the same for the 2 waters, while for the 3 water, it can be distributed in the whole surface. So that's very interesting. And I have summarized in the following figure. You can see the green line shows the sodium ions with 3 water molecules, and all the others is just very localized. So it's very interesting. We believe that we try to understand that by the very simple model, but I just skipped this one because the very limited time. And we can see that it's not just works for the sodium ions. We believe it also works for the magic number, also works for the other ions in the water. And here just summarized, you can see from the lithium to the different ions in the water. But of course, the magic number is different. So this is the result. Now, the paper just published a couple months ago, and there's highlights by different group peoples. Now, okay, let me give a conclusion. The take-home message is very simple. I think I can convince you that the water and the salt has been studied at the submolecular level by combined efforts, both theoretical and experimental. For example, we have shown that the inner structure of a water monomer. And also, we showed that the hydrogen bonding directionality for formed cluster. So this is really interesting. And even further, we can see that the full quantum properties is crucial in understanding the proton transfer and the single hydrogen bonding strength, and also the hydration of magical number on the interfacing transport of sodium ions. So that's a very interesting story, and I just try to convince you that the nuclear quantum effects plays the key role in the study of light materials. And finally, this is very important. I've been to thank my colleagues. Without them, I cannot go to verse today, and I thank the committee again. Of course, those are the really young stars in China and in any place. Okay, so the water is a very simple thing, especially if you look at the outside of the big ship, and there's a lot of water. However, my philosophy is the simple things done the right. Okay, thank you very much. I think the conference is quite interesting. There are people from, I just heard that, come from over 60 countries. And besides the plenary session, there's several parallel sessions. That means to give the young researchers more opportunity to present their work